Welcome to this explainer. Look, if you're a high-performance engineer or a technical lead, you already know the deal. You know the frustrating reality of standard AI coding assistants. I mean, one minute they're generating this brilliant time-saving boilerplate, and literally the next, they're hallucinating dependencies, or just quietly overriding your core architectural decisions behind your back. It's a mess. But today, we're going to talk about how to finally tame that chaos. Let's dive in.
This right here is the multi-million-dollar question keeping engineering managers awake at night. How do we actually stop AI from breaking our code? You've likely felt the pain of an AI hallucinating an entirely fake library, or suffering from severe context drift during a long coding session. Or maybe you've launched a monolithic agent aggressively refactor and just completely break your carefully established architecture. The truth is, standard, unstructured AI simply does not respect the boundaries of complex enterprise repositories.
So to fix this, we need a massive paradigm shift. Right now, most of us are having casual conversations with our AI. Standard prompting relies on this super fragile chat history, and as the context window fills up, the AI just straight up forgets your constraints. Instead, we need structured transactions. This means enforcing a rigid file-based state and making atomic commits. It forces the AI to treat software engineering as a disciplined transaction, transforming it from a flaky chatbot into a reliable enterprise-grade engineering partner.
If you take away just one thing from this explainer, let it be this core immutable philosophy of the ACE framework. Treat AI interactions as structured transactions, not casual conversations. Keep this in the back of your mind, because every single feature of the framework we're about to explore is built around this exact principle.
Okay, here's our roadmap for today. First, we'll break down the AI context problem. Then, we'll meet the ACE framework, dive into the shared project brain, explore the BMAD methodology, look at specialized agentic roles, and finish up with safety and regression guards. All right, starting with Section 1, the AI context problem. And really, why standard AI just flat out fails.
Without a rigorous container, standard AI prompting fundamentally fails in large repositories. I mean, hallucinations happen because the AI guesses instead of actually checking your documentation. Context drift occurs when an agent forgets what happened 5 prompts ago. It routinely ignores your established architectural patterns. And worst of all, you get a phenomenon called brevity bias. This is when the AI decides, for whatever reason, to rewrite an entire file just to fix a single typo, quietly deleting crucial logic in the process. It's literally an engineer's worst nightmare.
Moving on to Section 2, let's look at the solution and meet the ACE framework. So the ACE framework, which stands for AI-Assisted Code Engineering, is an IDE-agnostic framework designed for structured human-AI collaboration. Now, what's truly powerful here is that ACE isn't just some shiny external SaaS product you have to pay a subscription for. No, it lives directly inside your repository as a professional standard. It dynamically loads rules, skills, and constraints regardless of your local environment or which specific LLM you happen to be using today. It's totally version agnostic.
Section 3, the shared project brain. Let's talk about using your file system as memory. ACE completely solves that context drift problem by using your actual file system as the agent's memory, specifically the .ace and docs directories. They act as the immutable and evolving memory of your project. This means the AI isn't relying on a fragile conversational history window anymore. Think about it. If an AI agent joins a project on day 100, it has the exact same architectural understanding as an engineer who started on day 1, because the entire state is tracked explicitly in plain text files. Let's walk through this directory blueprint because it's pretty clever. The .ace/standards directory holds your immutable constraints. These are the coding and security rules that the AI absolutely cannot negotiate with. Then you have the .ace/skills directory. This holds procedural task knowledge, so instead of just guessing how to write a database migration, the AI loads up a precise step-by-step checklist. Next is the docs context directory, which holds your volatile, active session state, making sure handoffs between different agents are totally seamless. And finally, docs/ADR stores your append-only architectural decision records. By separating the immutable rules from the volatile active session, you completely prevent context degradation across your local workflows and your CI/CD pipelines.
Okay, Section 4, the BMAD methodology. Let's look at the core workflow engine.
BMAD, it stands for the Breakthrough Method for Agile AI-Driven Development. Basically, it forces the AI to actually think before it types, using a super strict pipeline. First, it has to analyze constraints. Second, discuss ambiguities with you, the human. Third, plan formally. Fourth, execute atomically based only on that specific plan. And fifth, verify. By putting a hard wall between the planning phase and the execution phase, this methodology entirely eliminates the AI cowboy coding problem.
And there's a golden rule with BMAD. Never, ever skip steps. If an AI asserts that the code works, well, that's just not good enough. During the verify phase, that assertion has to be proven programmatically by a dedicated script. The framework relies on an absolute rule, a verified.sh pre-flight and post-flight validation hook. This acts as your ultimate source of truth, guaranteeing that your repository maintains a perfectly clean state both before and after any code is touched.
Next up is Section 5, Specialized Agentic Roles. Why we need narrow atomic tasks. Look, monolithic agents given broad instructions inevitably lose focus the second their context windows overflow. ACE solves this by assigning very narrow tasks to distinct personas. Your new digital workforce includes an architect for planning, a developer for execution, a QA engineer for testing, and an incident responder for bug fixing. It operates exactly like a highly disciplined human engineering pod. By dividing the labor, you ensure system integrity isn't suddenly compromised by an overwhelmed, confused AI.
Let's zoom in on the architect persona for a second. This is the leader. They're triggered at the very start of a complex task. The architect is responsible for reading the specifications, checking regression guards, and producing a highly detailed implementation plan. And here's the kicker. The architect does not write production code. They solely define the what and the how before anyone gets to the do. For you as a high-performance engineer, this is a massive time saver. You no longer have to spend hours explaining system architecture to your AI. The architect handles that whole translation layer for you.
This brings us to a really cool formal feedback loop between the generator and the reflector. The generator is essentially the developer agent. It writes the atomic commit and outputs its reasoning. Then, in steps the reflector, an adversarial QA agent that actively looks for failures in that reasoning, trying to poke holes in it and distilling those failures into natural language lessons. So code is written and then instantly challenged by a competing persona. This drives up quality completely autonomously without you having to constantly babysit the process.
Finally, we reach Section 6, Safety and Regression Guards, how we protect your architecture.
This is the question every single skeptic asks right before deploying an autonomous coding agent into a real enterprise system. How do we actually protect our existing architecture from aggressive AI refactoring? Seriously, if an AI suddenly decides a core utility file needs a total rewrite, how do we stop it from taking down production?
The ACE framework's answer to this is the guard protocol. Every time a bug or an incident occurs, the framework forces a 5 whys root cause analysis. A formal RCA document is created, and, crucially, an entry is placed into a centralized file called regression-guards.yaml. This effectively turns every single bug into a permanent, file-based immune system response. Your project is literally actively learning how to defend itself from future mistakes.
And here's how rigorously that protocol is enforced. Step 1, a pre-generation hook forces the AI to check the regression guards file. Step 2, if a guard is triggered, the AI has to read the associated root cause analysis. Step 3, during any modification, historical invariance absolutely must be maintained. And Step 4, a post-generation hook runs very specific regression tests. The AI physically cannot merge the commit unless these checks pass. It's not a suggestion, it's a completely non-negotiable pipeline step.
When you combine the shared project brain, the BMAD pipeline, those specialized agentic roles, and strict regression guards, the result is pretty profound. Regardless of your underlying IDE or which LLM you prefer, AI interactions stop being a chaotic roll of the dice. The ACE framework bridges that massive gap between raw text generation and disciplined enterprise-grade software development. Your team's velocity goes up, specifically because your system integrity is fundamentally locked down and protected.
As we wrap up this explainer, I want to leave you with one final thought to consider for your own repositories. Tomorrow morning, when you open your IDE, will your next AI interaction be a casual conversation or a structured transaction? Which one you choose is going to dictate the stability of your entire codebase. Thanks for joining me to unpack the ACE framework. Happy engineering, and we'll see you next time.